Didn't I need to be somewhere today? Oh, that's right. I need to get to RailsConf. I better hurry. Hi, Abby. I gotta get to RailsConf. Hi, everybody. Welcome to RailsConf. All right, I just need to get my jacket off here. Put on a microphone. All right. Hello, everybody. Okay, sorry. Hi, everybody. I'm so happy to welcome you to. HeyConf, the conference that should have been an email. But seriously, welcome everybody to RailsConf. I'm so happy that I get to be opening the conference again this year. My name is Patterson. I'm also known as Tenderlove on the internet. I've changed my icon, so I look like this now. This is my icon on the internet. I work for a company called Shopify. I'm a full-time Ruby and Rails contributor at Shopify. Shopify invests in the technologies it uses, and we use a ton of Ruby and Rails. Our team, my particular team, works on improvements to Ruby and Rails, like speed improvements and new features. We're currently working on a JIT implementation for Ruby, and as well as some improvements to Rails, like deferred queries, which I'm going to be talking about later in the presentation. As Megan said, I'm on the Ruby core team and also the Rails core team. And as a good a good representative of the Rails core team, I have to point out that this is in fact not an octopus leg. It is like a railway track. And now that you have seen the octopus leg, I'm sorry, you cannot unsee it. It's great to be here on March 422 of the great year of 2020. But seriously, I really hope to be seeing all of you in person this year. Actually, I thought when I found out we were doing this conference online again, I thought I was going to be recording it. But I guess that's not the case. I got an email from the organizers saying, "Hey, when is your recording going to be ready?" But I was in the list, like the mailing list with all of the other speakers as well, and I'm like, "Oh, okay, I'll have the recording already." And they're like, "No, you're doing it live." So I guess I have to do it live. But I have a pretty hard time like giving a presentation without a live audience, so I decided to bring a few guests. So I have some guests here, including my cat, my other cat, and also a few mystery guests. Though one thing I really do like about having the conference online, like I wish I had been able to meet everyone in person, but one thing I like about having it online is that I'm able to take selfies with all of the keynote presenters. So I got a selfie here with DHH, was really great. I also got a selfie with Brian Cantrell. This was a good time too. I was able to meet Eileen and get a selfie with her. Hi, Eileen. And I was actually also able to get a selfie with me and Brian. And I was really excited when during his presentation when he said, "But at what cost?" So I got a selfie with Brian. But at what cost? Anyway, I was also able to get a selfie with myself, which is a really like special treat. So I gotta do one thing here. One thing, okay. Gotta make this pose, okay. All right, I had to do that so that we didn't rip a hole in the fabric of time. Because I guess now that you're looking at this, how did he get a selfie with himself during a presentation? Is this presentation actually live? I'm sure you're wondering if this presentation is actually live, and I can guarantee you this. I promise all of you that this is definitely a live recording. Okay, it's a live recording. One other thing I like about having online presentations is that I get to enjoy all the talks pre-recorded and released at the same time, and I can watch them at 2x speed, and that makes me really happy. I know that I can know that I'm a 2x developer. And also I've learned from this that I am definitely not a 4x developer. I can't do that. But speaking of the pandemic, I know that it's changed everybody's lives, including mine. We're all doing a lot more working from home these days, and everybody has been doing a lot of work from home, and this can really lead to like some awkward situations. Even for me, like I was working from home before the pandemic, but this has really impacted my life as well. I mean, so really awkward stuff can happen, and it can interfere with your life in ways that you didn't expect. But one thing that you have to do, I personally do, is make sure that I have a good Zoom background. So I've made a bunch of collection of Zoom backgrounds. Like I think a lot of people like to use nature or patterns, but I like to keep my Zoom backgrounds more real. I use a Zoom background of my own office like this, and I'll give you a little preview what it looks like. So this is what it looks like when I'm in chat. So I'm like this. So you can see that I have a nice person helping me with my chair here. All right. I also bought a green screen and a lighting setup so that I could do like really nice videos and show you nice things, make fun stuff. I also bought one of these things. Like it's like a selfie stick that I've used exactly once, and all of you have seen the fruits of my labor. The other thing I've been doing is I've been baking a lot of bread. So I learned how to bake bread. This is some bread that I made. Here's the crumb of the bread. I gotta show it off. I think I did a pretty good job. But of course I need something to go along with the bread, so I started making cheese as well. This is a cheddar that I made. I've also been making camemberts. I really enjoy making camembert. It's delicious, really good cheese. But I want to share something about it, a little bit about it. I aged the cheese in my basement, and this is a drawing of like my basement from the top down. So I have two cheese fridges, two cheese aging fridges, and they're sitting right there, and like kind of close to it is a central air unit, and I have to flip the camembert once a day. And when I do that, I open the fridge up, and it kind of like the smell kind of comes out, and unfortunately it makes its way over to the central air unit, and then it like makes its way all throughout the house. Now, some people in the house, namely me, enjoy this. They think it is very nice. However, other people who live here, they're not so excited about this feature. But here's another photo of one of my camembert, and one thing that's really cool about it is if you cut a wedge out of a camembert, it looks like a pie, like it looks kind of like a pie chart. And I discovered that apparently in France, people say camembert to refer to pie charts, and I thought that was cool. Like, I personally love camembert more than pie, so I wish we would call them camembert charts too. I've also been getting a lot into electronics. Getting better at electronics. This is a Wi-Fi based temperature, humidity, and air quality sensor that I built. And here's a dashboard. The dashboard for it, so I can keep track of the air quality in my house. And of course, I called the server that hosts all the data. It's called Tenderhome. Oh. Also, one thing I forgot to mention, in addition to, okay. So here's a URL for the sensor. You can go look at it and like build your own. Now note that it does not detect cheese smell. One thing I need to point out to all of you as well. So I got the green screen, I got a lighting setup. I also got this thing here, which is a MIDI controller. So, and what's really nice about this thing is like, it's much better for me to give a presentation in front of an audience. So what I set this up to do is if I make a really good joke, I can do this. And and if I make an even better joke, like a really, really good joke, I can do this.
Boo.
So yes, in addition to cheese smells throughout the house, I've been testing this too, and I can tell you, everyone here is super excited about it. All right, so the other thing I've been doing is, like, I read an article. I read an article. Sorry, I read an article by Paul Graham that said that everybody gets rich by making startups. So I took this to heart. I mean, he's always right. So I decided I gotta make a startup because I want to be rich too. It sounds great. So I've made a startup and I call it Tender Love's Tender Lab. And I want to present to you some of the products, that we've been working on. So the first one here is the first product that we developed. We developed this last year. It's called the Analog Terminal Bell, and I'm going to play the ad for you now. Let's see. Let me pull up the ad. Has this ever happened to you? CD space GIT tab. This must be the right directory. If only I'd heard the terminal bell. With the Analog Terminal Bell, you'll never miss a terminal bell notification again. The Analog Terminal Bell is a bell that rings anytime a bell character is displayed on your terminal. Simply plug it into USB. Then enable the Analog Terminal Bell in your terminal settings. It works with your shell. It works with Vim. It even works with DevU Random. Thanks to the Analog Terminal Bell, I'll never miss a terminal bell notification again. Go online and get yours today. Go to analogterminalbell.com today to get your very own analog terminal bell. Once again, that's analogterminalbell.com. Analog Terminal Bell is not actually for sale and requires a custom build of iTerm 2. Other restrictions may apply. See website for details. Okay, so that was the Analog Terminal Bell, and that I developed, or excuse me, our really big team developed this product last year. We've been working on a new product, and I want to share it with all of you today, and it's what I call the analog carriage return. Now, I'm sure many of you have had this problem. You're typing away, and all of a sudden your code gets to the 80th column and you're like, oh, like you went past the 80th column and you didn't even notice. You're like, how did this happen? Now I have to go back and reformat my code so that it's less than 80 columns. This is a huge waste of time. So that's why I started developing this product. That's why our team started developing this product. Now I'm going to show you a demo of it. This is just currently a sneak peek. We're finishing up the hardware solutions. We're going to do a full release later on this year, but I just wanted to show you a demo of it. All right, I'm sure all of you can appreciate how useful this would be in your day-to-day programming activities. So, sorry. Moving on. Brian Cantrell spoke about the history of computing. I mean, specifically, like, he was talking about Moore's Law, and I thought, if I'm like, I should talk about the history of the carriage return too, since I'm selling this product. So I thought maybe today I would just take a couple minutes here to talk about the history of the carriage return. So we've frequently seen these two terms together, the carriage return and the new line, carriage return / new line. And actually, this term originated back in the 1880 BCs here in the Wild Wild West. So in the ancient Wild Wild West, people actually had to ride in horse-drawn carriages. Now, not everybody could afford their own carriage, so it was very common for people to do ride sharing back then. Now, what would happen was the horse-drawn carriage would come pick people up, take them to their destinations, and then it would return to the original stop. And when the carriage returned to the original stop, people would line up again. And this is how we would get a carriage return and a new line. So how does this relate to computers, though? Like, these are horse-drawn carriages and people lining up. Well, actually, back in those days, calculations were all done by hand, and the ancients usually used what was a piece of wood with some graphite embedded inside of the wood to do these calculations. And I actually have one of these instruments. I'm going to give you a demonstration here today. So this is an example of a calculation being done. Now, they would actually use these computers for more than just math problems. I'm using it for a math problem here. They would also use them to keep track of people that wanted to ride on the carriage. So here's an example. You can see that we have a carriage return that is followed by a new line. Now, the really important thing is that ever since Apple invented computers, we've been able to move all these calculations into the digital space, as you can see here. So now let's go back to my presentation now, like my presentation. I strayed a little bit off of topic here, and I want to talk about my stuff today. So if you've seen any of my talks in the past, you'll notice that I have like kind of a format that I go by. Usually I do this. I'll do an introduction. I'll do really good jokes. Really good jokes. Oops, no, not that one. I'll do some really good jokes, and then I'll have a technical part, and then I'll go to an ending. Now, fortunately or unfortunately, today I have I have to give a 90-minute presentation. So I've been struggling with how to fill that amount of time. So this year I decided to add a new section. Now, I know this is a very long presentation, so yes. 90 minutes is a long time. So I added a new section and I call it the Ranting Section. I figured since 90 minutes was so long, maybe I could pick like some axes to grind, or maybe like some bones to pick, or another synonym for complaining, or something so I could fill up 90 minutes of time. So I guess I seriously am going to complain. Okay, let's do this. So actually, the first thing I want to talk about is stability. I've seen some tweets on the Twitter of people saying stuff like Rails is unstable, and I kind of see this as a meme, like, oh, I don't know, Rails is unstable, it's so hard. Whenever we upgrade, things are bad, and I don't think that it's true. Like, I don't think Rails is unstable. I think Rails is very stable. I mean, like, I think what people are actually saying is it's hard for me to upgrade. So, I mean, I don't think like Rails is randomly crashing or shaking underneath our feet. And this sentiment of Rails being unstable kind of bothers me for a few different reasons. The first reason is, like, this is kind of a personal reason, but we try very hard not to break stuff. So, like, we as a team do not want to break your application. We absolutely don't. So we do our best to make sure that it will work well and you can upgrade. Now, the other thing I was thinking about, which is more of a, I guess, like, bigger picture issue, is like, if you think about the gems that are in your gem file, like, think about any of the gems that are in your gem file, like, and the responsibilities each of those gems have. So, for example, like, Nokogiri parses XML, StackProf does profiling, I18N does internationalization. Now think about Rails and all the things it does. It has to deal with requests, responses, rendering templates, making database queries, doing a whole bunch of different things. Like, the API surface area of Rails is huge. It's really big. So if we think about this API surface area, and then maybe the bugs or issues, any other issues that come in, like I'm just calling it borkage because I don't know what to call it necessarily. If we take those issues and divide it by the API surface area, I think that we would find that Rails is as stable or more stable than most of the gems that we work with. Now, I actually went through and did these precise calculations, and I found that this ratio for Rails is actually 0.001, and for other gems, it's 0.01. And I mean, I'm no scientist or mathematician, but these numbers tell me that Rails is actually 10 times more stable than other gems. All right, so actually, I think what the issue is that we have kind of a big bang type upgrade when we're upgrading Rails. When we upgrade Rails, we're upgrading tons and tons of stuff at once. It's not just one particular part. So even though like we do our best to keep that breakage rate low or keep that rate low, the probability that you'll hit a bug is still fairly high because we're upgrading so many things at once. Now, the only thing I can think to mitigate this issue is kind of an incremental upgrade. Something that would allow us to keep the APIs that we changed low, like the upgrade API surface low, but we don't have a very good way to do that right now. So if your company has the resources like we do at Shopify, and I know GitHub does this as well, is if you can track main, so if you can track Rails main with your application, then you can upgrade just a few commits at a time. Now, this might sound a little bit scary, but we also we, the Rails core team, try to make sure that main is pretty stable so you can run it in production. Now, I realize like a lot of companies don't have this resource to be able to do this type of incremental upgrade. So I really recommend keep up with the point releases. We really do our best to make sure that the point releases are stable and easy to upgrade. And as soon as you get to the end of that point release, go to the next major release. Of course, it's not going to be perfect, but you know. The other thing is, if you run into any problems upgrading, please report those incompatibilities. If your app breaks, tell us, but I mean, also try to fix it. We definitely take patches that will fix backwards incompatibilities. So we really try not to break things, and if we do, it may be a mistake. Yes, I said this. So I guess the main point is that we try hard not to break stuff, and folks that can run their apps against main, please do it. We'd appreciate any feedback we can get on the main branch. That way, everybody can upgrade or everybody can take advantage of the work done against main. So the next thing I kind of want to complain about is web apps being I/O bound. Lots of people say that web apps are I/O bound, so we don't need to worry about the speed of our language. In other words, we're spending most of our time doing database queries or reading from sockets, writing from sockets, reading and writing to files, for example. Now, this doesn't sit easy with me because I also hear stories about people who rewrote their application in a different language and made it got faster. But the problem with that is that I/O is the same speed in all programming languages. Reading a file in Ruby isn't any slower than reading a file in Go, for example. Doing a database query in Rust isn't going to make the database return any faster than it would in Ruby. So this doesn't sit well with me. There has to be some other explanation for it, and I think either we have an unfair comparison, which I'm going to address later, or I/O isn't actually the bottleneck. My guess is that Rails apps spend more time in CPU than we think or we want. So I think what we really want to say is that ideally web apps are I/O bound. Now, I think the reality of the processing looks something more like this, where we have a situation where we're spending most of our time in I/O, but still some of our time in the CPU. And as time goes on, we get blocked. We don't get to do those I/O bound operations because we're waiting on CPU operations. What we would prefer to have is something like this, where we're able to do I/O and CPU in parallel, so we can get blocked on those I/O calls. So we really are spending all of our time in I/O. So I'm going to return to this topic in a little bit, but my main point is that I really think CPU time is important, and we need to be working to improve Ruby and Rails in that area. Now, another side note is that I want to point out that Ruby does in fact have real threads. Some people ask me about this. Ruby can perform things truly in parallel. For example, this code here, let's say we have a file and it takes 10 seconds to read that file, just an example. If we do that 100 times in 100 different threads, this code will actually only take 10 seconds. It's able to do this truly in parallel. Puma and Sidekick take advantage of this because what they do is Puma is a threaded web server and Sidekick is a threaded background job processor. They take advantage of the fact that Ruby can do I/O operations totally in parallel, and they're able to do more processing with lower overhead. Now, one caveat is that in MRI, CPU-bound operations cannot be done in parallel. So for example, in this case, if we calculate Fibonacci sequence and it's really expensive to calculate it, we won't be able to do all of these in parallel. If you have an application that is CPU bound like this, maybe look at using JRuby or Truffle Ruby. Now, if web applications are truly I/O bound, and Ruby can trivially do I/O in parallel, then rewriting the application shouldn't make any difference. So this is where I want to get to the next thing I want to complain about, which is application rewrites. And I hear stuff like people say, "Oh, I rewrote our application, and we rewrote our application in Fortran, and now it's way faster." And that seems fine. Like, okay, that's fine. I'm sure people experience this, but I don't think that you can draw many conclusions from it. And the reason, or the problem, is that we learn from our mistakes. And I think it's funny that I'm saying, like, I can't believe I'm saying the problem is we learn from our mistakes. But the issue is that since we do learn from our mistakes, our rewrite will never be an apples-to-apples comparison with the original. And yes, I am using a peach emoji here because it looks like a butt. And I said butt. Anyway, our new application is tainted. Our new application is tainted by the knowledge that we gained from the first iteration. All we can say is that we rewrote the application and now it's faster. We can't use this information to make any judgment calls about the previous code. The other thing is, even once we've rewritten, it's actually all downhill from there. Weeks after we finished our shiny new rewrite, we'll find missing business requirements or new business requirements, and the system will get bogged down and slow regardless. I mean, when we reinstall macOS, yes, everything is great and fast, but then reality hits and we have to install Slack and Chrome and all these other applications to do our jobs, and all of a sudden it's slow again. You could say to yourself, well, I don't know, at least it's faster than it would have been. Well, like, we rewrote this in Go, so it must have been faster than if we had done it in Ruby. Maybe it's true, and maybe that isn't. We don't know because we couldn't do a fair comparison. But the real question is, are you happy? You have to ask yourself, was that speed improvement that may or may not actually exist worth my happiness? And personally, I think that we need to be optimizing for happiness. We should be selecting the language and framework that make us productive and happy at our jobs instead of rewriting so that we can gain some unknown amount of speed improvements. So what I want to say is that I think people should learn to profile. We should be learning to profile our code and learning to optimize our code. And if we do that, we can end up with faster applications and a faster framework and maybe even a faster language. So I like to say this stuff, but I also have to admit that it's kind of a difficult sell for engineers because, like, doing performance work is much different than doing feature development. It requires a different skill set. And I would say that it's also not as flashy as doing feature development. And I want to address both of these problems. And the first thing is, like, I want to speak to you developers in the audience that anybody can do performance work. All of these programs were designed and created by humans, and we are human too, hopefully, so we can learn and understand and eventually do any of it. The other thing that we need to do when we're trying to sell this performance work is we need to make it flashy. We have to tell a story. Like, how did we investigate this issue? What kind of evidence did we gather? What kind of impact did it have? Were we able to improve requests per second or lower memory usage? And I think that this can expand not just from performance, but also into just doing development on legacy code in the system. For example, like, maybe we were able to make changes easier for the rest of the team. Maybe due to our refactoring, we were able to improve the productivity of other feature development teams. Now, I guess what I'm trying to say is that features sell themselves Like you can say, hey, go look at this feature. I can click a button now. It works. It's great. But perf needs a little bit of help. So we need to be strategic in the way that we sell it. All right, let's talk a bit about Rails now. I'm done complaining, I promise. Let's talk about Rails. And as somebody, as somebody that is interested in performance, I usually don't have any flashy announcements to make at Rails, but I do want to mention a couple, or at RailsConf, I do want to mention a couple new things that I am really excited about that are coming in Rails 7. The first one is async queries. You can go check out the pull request at this URL. Earlier I was talking about making our apps I/O bound, or trying to get them to be I/O bound, and this is a feature that really helps address that issue. It was originally done by Jean Boussier, who's on our team at, who's on my team at Shopify. This feature allows us to defer queries. So here's an example usage, and what happens here is the query is added, like we say load async at the end, and the query is added to a pool and executed in a background thread. And what's nice is when we access the data, either the data is already loaded and we can use it, or it will wait until the query executes. And either way, it's totally transparent. So this is a way for us to say, like, I know I'm going to need this data eventually, not right now. Please go load it, and then later on use it. The next thing I want to point out is a smart preloader. This was written by Jay Hawthorne and Dinah Shi. They're both at GitHub. I want to show this off. This is one of my favorite features, and the reason I like this feature so much is because you don't have to do anything to use it. It just works. This feature impacts, it's called Smart Preloading, and this feature impacts the preload function. Now, so here we have an example where we have an author that has many posts, and then the author model also has favorite authors, and the favorite authors also have posts. Now we're trying to preload posts in two places. Now today in Rails 6, this would have done two queries against the post table, but with smart preloading, it knows that, hey, we're going to be doing two queries against the same table, so it reduces it down to only do one query. And I really, really love this because for you to take advantage of this feature, all you need to do is upgrade. I know I talked about upgrading being difficult, but yes, just upgrade. Oh, hold on. Yeah, good feature. Okay, the next one I want to talk about is a faster Constantize. Again, this is done by Jean Boussier. Constantize is just faster. That's it. It's just faster. It's 5 times faster. If you constantize something, it's 5 times faster. That's it. But the reason I wanted to point this one out, I mean, it's really great that we get this performance improvement, but the reason I wanted to point this out is this particular feature actually took 9 years to do. And I want to give a little bit of history on that. Back in 2012, I added this function. Like we had been talking about, oh, we'd really like it if when we do constantize, we could just ask Ruby to look up the constant for us. And prior to Ruby 2.0, you could do const get like this, but you had to pass in like just the last name. So in this particular example, you could only pass in like foo or Baz. You couldn't pass in the whole string like this. So I lobbied and got this feature added to Ruby 2.0 so that we could just say like, okay, I'm going to pass you a string and then this will give us back the constant. Now, unfortunately, we couldn't use it, turns out. We couldn't use it because we couldn't autoload, like it didn't go through require, which means that it wouldn't autoload the constant, and unfortunately this meant we couldn't use it in Rails, which was very embarrassing for me because the entire reason I introduced this feature was so that we could use it in Rails. Please don't tell Matt. So once we realized this, I added another feature in Ruby 2.3 in 2015 that lets us dynamically change. So here's an example of autoload. Before Ruby 2.3, this autoload call would not go through Ruby's regular require process. So what would happen here is if you tried to access this bar constant, it would go through Ruby's internals and load that file on its own, and there was no way to intercept when that file got required, which means we don't know, like, Ruby gems couldn't intercept the require to look it up in a gem, bundler couldn't do the same thing, and we, on the Rails team, we wouldn't be able to intercept this call in order to deal with constant loading. constant loading and reloading. So I introduced a patch that all it did is when we call, like when a file is required via autoload, it actually calls back into Ruby's require, and that allowed us to intercept the call and then do something with it. Now, I have to admit, after we completed this, or after I completed this patch, I forgot why I was doing this. So then it just sat there for quite a while until 2019, when Xavier from the Rails core team noticed that, hey, we can intercept autoload calls, and he wrote Zeitwork, which allowed us to do all of the constant reloading and constant missing behavior that we do in Rails. Also, around the same time, a bug was fixed in Ruby 2.7, and I'm going to show you the weird bug fix. We also needed this as well. So what happened was in Ruby 2.6, this code here, so we have module foo, module bar, and when we did a const get in Ruby 2.6, this would return bar, and in Ruby 2.7, it returns a name error, which is what we want. So what would happen is, like, I find the Ruby 2.6 behavior to be kind of confusing, and I'm glad that we fixed this. What would happen is we would try to look up the bar constant, or Ruby would look up the bar constant. It didn't exist on foo, and then it would go, okay, well, it doesn't exist on foo. Now I'll go look it up on object because object is foo's parent. I'll check that. And then, of course, bar is defined on object, so it gets returned. That is the behavior that we do not want. Now, all of this stuff put together, like Jean built on top of this and was able to put together this pull request here, which turns Constantize into one single line, which is exactly this. So here is the new implementation of Constantize in Rails. It took us 9 years to delete 32 lines. So like 3 lines per year, but I think it's worth it. And that, of course, is the power of open source. 9 years. Actually, no. This is a clap one. I think we should clap on this one. Clap. Yes, I think this is good. All right, the next thing I want to show off is that we actually removed all of the magic from Rails. Like, I feel like a lot of people complain that there's too much magic in Rails. We actually removed it all for Rails 7. This is definitely a clapping feature here. No more magic. Here's the commit right here. George removed my magic and replaced it with mini mime, so we no longer have magic mimes in our code base. Now we just have mini mimes in our code base. Wait, I'm gonna okay, I'm gonna add a Okay, so the next topic I want to talk about is a bit to do with humility. I think, like, we come here every year, we talk about how great Rails is. I've been up on stage here talking about how great Rails is, and I wanted to do something. I wanted to be a little bit more introspective this year, and kind of like, I don't know, look at some code inside of Rails that would make us all laugh. So I wanted to find stuff in Rails, or weird code in Rails that looks like this. So this is an example of a constant from Spring, simple bean factory aware aspect instance factory. So this is a real code, and here is another one like this constant from aspect J has this type. Actually, I'm not going to try and read it. I'm just not going to read it. I wanted to find like weird code like this in the Rails code base, stuff that made you go like make this face. So I thought up a few heuristics for things to look for, and we're going to dig into them here. And I promise that these things will at some point relate to Rails performance, and we'll talk about the Rails performance later. So I only had 2 rules. I only made 2 rules for this exercise. One, I only want to look at Rails code itself, so no dependencies, and no code in the application. So only Rails itself. Also, I don't want to look at test files. We're allowed to write any kind of wild code and test files that we want. Like, that's fine. We don't want to look at that. Also, hopefully the test cases in Rails are not impacting, hopefully you're not loading any Rails test code in your Rails application. If you are, don't do that. So I'm going to do my best to describe how I found these weird things, because I think that the journey to finding them is also as interesting as the stuff that we find. And I'm not going to be using static analysis for this, mainly because I'm lazy. So my strategy for analyzing the code base was, I thought, okay, what I'm going to do is I'm going to load as much code as possible, then introspect on everything that's in memory. My first idea was just to iterate through all of the directories in Rails and then load every single file. So here's the code I used for that, and it turns out it's actually hard. Like, you don't need to read this. I threw this away because it doesn't work. It's much harder than I expected. Some of the files in Rails are JRuby specific, and of course I'm using MRI, so I couldn't load those files, it would break, so I had to skip those. And then some of the files, when you try to require them, they just raise a name error because the loading matters. So I decided, okay, what I'll do is, if it raises a name error, I'll defer it, and then load it later, and then load other stuff, and then try to load those later. And unfortunately, like, even though I deferred them and tried loading them, like, I ended up getting into an infinite loop, so it didn't, like, that didn't work. So then I decided, okay, let's just make a Rails application and boot it in production mode so that everything gets preloaded, because if we load in production mode, stuff gets preloaded, and I know that that path works. Like, hopefully we're able to write a Rails app and run a Rails app. So since we don't care about application, like, I don't care about app code, I just wrote a basic Rails application. And the main strategy that I want to do is just boot the app in production mode so that everything is loaded. Then I'll do a gc.start to eliminate any garbage objects that were allocated during the boot process, then iterate over all the objects in the heap and try to find objects with weird stuff on them. And I'm going to show the code, like, I'm going to show the code for finding statistics, but for the rest of the slide, I'm going to omit, like, I'm not going to show app boot stuff and other things we know about already, just to keep them short. Anyway, when I wrote this slide, I thought to myself, yeah, this will totally work. Like, no problem, this should totally work. And unfortunately, it did not. I love the soundboard. All right, so what was the problem? The first problem that I encountered is we only want to find code that's defined in Rails itself. So how can we do that? The first thing that came to mind is, say, let's use method source, like the source location on methods. We'll get the methods off the class, ask the method for the source location. So, for example, we can go through all the classes that are in object space, ask the class for its methods, then check the source location of the method. But this has a couple drawbacks. First, we have to allocate a whole bunch of method objects, so this could be expensive and take a long time. And of course, like, this is serious code we need to execute very quickly. And the second is that, what if the class doesn't have any methods on it? So if the class has no methods, then we won't be able to know where it was defined, and I don't want to exclude those classes. So it'd be nice if we could get the source location of the class itself. And we kind of can do something. There's a feature called const source location, and this is how you use it. But it has a couple of problems. So first off, we need to know the name of the constant that we're trying to fetch. So we have to be able to get this name here. So we have to have B, this example. And the other problem is we have to know the outer scope of the thing that we need to get. So we have to get what I'm calling like a namespace here. We have to get that top level thing. So we have to know about A. Now, unfortunately, if you look at the code that we're using for walking the heap, we don't have that information. We have neither of those things. So you can ask the class for a name, like you can say, hey, class, give me your name. But the problem is sometimes it'll return nil, like if it's an anonymous class. Sometimes it'll do the right thing and you'll get a class name back. Or sometimes, like, the class can implement the name method and return just stuff, like whatever it wants. So on top of that, like, we need to be able to get to its, like, outer part, the outer level, so that we can ask the outer level for the source location of this particular one, which means, like, we would have to parse the constant name, and of course we know, like, we can't necessarily trust the name method. So what I decided to do to get around this is essentially to fix Ruby. I submitted a patch to Ruby that implements source location on constants. So you can say, like, hey, class.source, not on constants, on classes and modules. So you can say class.source location. This is the example here. So now we can say, like, hey, class or module, give me your source location. And then this will allow us to filter out all of the constants that are just inside of Rails. Okay, then the next issue that we had is, eager loading. It turns out that eager loading is actually a lie in Rails. When you boot into production mode, everything from your application will be eager loaded, that is true. But that doesn't guarantee that everything inside of the framework will be loaded too. So I'm going to show you, I'll show you an example here. So let's look at this. This program, what it does is it takes a copy of all the loaded code, like all loaded features is a list of all the files that have been evaluated and loaded. Then we're going to check a random, we're just going to check this constant, we're going to print it out. Then we're going to print out the loaded file. We're going to take a difference between the loaded features and the copy that we took before. And if nothing got loaded, then we should get an empty array back. If something got loaded, then there will be a new entry in the loaded features, and we'll see that the array is not empty. And unfortunately, when we run this in production mode, we can see that referencing the statement cache class actually loads a new file. So eager loading is a lie. We're not actually loading everything. Now, of course, this actually makes sense. We don't want to load everything. For example, like, you don't want to load the Postgres database driver if you're using MySQL in production. Like, that doesn't make sense. But I do think that we should be able, like, we should probably examine from time to time what is and isn't eager loaded. Like, for example, this thing, like, if you're using Active Record, you're probably going to be using the statement cache in production regardless of the database that you're using. So we should probably be eager loading that. So this example that I showed, we probably need to start guaranteeing that's loaded when you say eager load. So the best thing that I found was, okay, we're going to run some requests through the application to get as much code loaded as possible, and then analyze that. And I'm going to spare you the details of exactly how I ran those test requests through, but it did require a bunch of code. I mean, yeah. So looks like we have a question here. Yes, you in the back there. All right. Yes. Hi. Great presentation. I'm a huge fan. Oh, thanks. Thanks. Wouldn't static analysis have been much easier? Yeah, that's a great question. Static analysis. Yes, at this point, yes, I do think static analysis would have been an easier option, but I am not going back and redoing all of my slides, so we are going to continue with this. So the first question I asked is, okay, what is the longest class name? So I went through and found all the classes that were defined inside of Rails, and these are the longest names. So this is the top 20 longest name. And the top one is action controller, request forgery, protection methods, null session hash. And I looked up what this function is for, or what this class is for, and this is if you want to have CSRF protection, but no actual session is associated with the user, you'll use this. Now, unfortunately, I don't think that this is as funny as the Java classes we saw earlier, and I realized that the problem is we actually have like all of these colons in here that are separating the name. I think that makes it somewhat less funny. What we really want to do is we want to see the longest string of characters put together. What is the longest string of characters? So I changed it. So instead of sorting by length, we would sort by longest contiguous string. So here are the classes with the longest contiguous strings, and this is how I discovered my favorite new class, which is, I'm pleased to present you with active record has many through can't associate through has one or many reflection. Yes, I think it's a laugh. So I went and looked up this this class definition, and this is the class definition. It's empty. There's nothing in it. So yeah, we needed to have that source location on modules in order to find this thing. Now I looked up its parent class, and this is the parent class. You don't need to read it. Like, don't worry about it. Apparently has many through can't associate. Has many through can't associate through has one or many reflection is actually an exception class. It's an error. And I think that's funny. Like, we usually add errors at the end, so I feel like the correct name should have error at the end. But I mean, can you imagine getting this exception, like an exception name this long? I Googled it and I found many unhappy posts on Stack Overflow with this constant name in it. All right, so the next thing I wanted to look at is what is the longest method name? We did class names, but how about method names? This one's pretty easy. All we have to do is look at all the classes, get their methods using the instance methods method or the method, and then we pass in false so that we don't get parent classes and sort them by name, no problem. This is the list. This is the list that I found, but something seemed off to me. Like when I look at the source location for the first method, like the first method is autosave associated records for preview image attachments. I looked at the source location and I found this. It looks like this method is being metaprogrammed using define method. Also, it's defined inside of a method called define non-cyclic method. Now there's two things that I think are very, two things about this. First, I think it's pretty weird to have a method called define non-cyclic method. Like what does cyclic method mean? When I looked into it, what it means is recursive. So why didn't we just use the word recursive like normal? We're defining a define non-recursive method. Now the other thing that's weird about that is like, if you're defining a method, shouldn't you know whether or not it's recursive? Like I feel like if you're defining a method, you should be pretty sure about whether or not it's recursive. But I guess like I'm sure there was a reason for this. There's always a reason for it. I just don't know what it is. And when I find out the reason, it will be a good reason, and then I will have to eat my words. But anyway, these aren't the things that I really wanted to point out about this code. The issue here, in my particular case, is that we've metaprogrammed a method with a long name, and I don't care about that. Like, I'm not interested in that. Anybody can metaprogram a method with a long name. I want to find the method that somebody actually sat down, typed it out, got RSI because the method name was so long. That's what I want to find. So I want to know about physical typing. So the question is like, how can I tell if a method is metaprogrammed? Like that was a very interesting question to me. So, but first I want to define what I mean by metaprogramming because I think it's a little bit different in this case. So what I actually want to find is I want to find methods with mostly dynamic names. So for example, here I want to ignore these first two cases because we have a defined method with a string inside it. We're doing string interpolation there, and I want to ignore the eval because we're doing string interpolation there. However, I do want to get the method, the normal method, we want to catch those, and I also want to get these attr readers. Now, attr readers, attr accessors, I want to get those too. And the reason I want to get, like, those I think are traditional, we would consider those to be metaprogrammed, but the reason I'm interested is because somebody had to actually type out the whole name. Like I want to know about those. So my first idea was like, okay, let's group by source location. So if some loop is defining a bunch of methods using eval or define method, they're going to generate a bunch of methods that have the same source file and source line. So we know that if a bunch of methods share the same line file and line number, it's probably a metaprogram method. But unfortunately, the same thing is true for attr accessor, and I do want to count those. Like I do want to find those. So the next thing I thought about was, okay, what if we could examine the instruction sequences of the methods to see, like maybe we can learn something from that. This class here, RubyVM instruction sequence, gives us access to the compiled instructions for a method. I thought maybe I could use this to differentiate between different methods, and it turns out I actually can. Regular methods, methods defined with define method, and eval methods all have instruction sequences. But methods defined with attr accessor do not. They don't have any instruction sequences associated with them. So all I had to do was exclude methods that share source location and have instruction sequences. So here I had my algorithm. So here So here is my code for finding the longest non-generated method name. So what we do is we get all the methods, we group all the methods by location, then we keep all of the non-generated method names. And this is the top 20. This is the top 20 list. I think I guess it's kind of anticlimactic, but it is telling that probably like 50% of these methods have to do with security. Like all of these ones here that are highlighted or that are darker, those are all methods dealing with security. The other interesting thing is I took all the methods in Rails and broke them down by type. So here's what it looks like. Here's a chart that shows all of the methods broken down by type. Broken down, when we break it down in this way, most of the methods in Rails are regular methods with only one definition location, and a small percentage of them are attribute attr accessors. Now, a pretty large amount of them are generated, and I think a lot of these methods are actually generated delegate methods. Like if you do delegate blah to blah, but I couldn't come up, like I couldn't figure out a good way to differentiate, like to detect methods defined as delegate methods. All right, so the next thing I wanted to look at is longest palindrome method, like what method name, what is the longest palindrome we have? Unfortunately, it's level, which I was kind of disappointed about. Like I figured we would have something better than that, especially like, I figured we could do better, especially given that race car is a palindrome and DHH drives race cars. So like, why do we not have a race car method? Seems like an easy win there. I forgot I had that transition in there. So then I wanted to know what class has the most ancestors. Okay, does anybody here know which class has the most ancestors? Okay, yes. You here in the front? Yeah, you.
Hi. Really great presentation that you've got going on here.
Thank you.
I'm going to guess active record base is the one with the most ancestors.
Sorry, no. Actually, the top is active storage blob. It's funny that there are so many. So this is interesting. This is the top 10 classes by most ancestors. So what's really interesting here, actually, what I think is interesting about this particular chart is that it's dominated by classes from active storage, and I think that's funny because my particular test app doesn't do any active storage stuff at all. So I thought that was kind of funny. Somehow database like the database handling isn't preloaded, but apparently active storage gets preloaded. So actually, active storage blob inherits from active record. So you in the front there, you're almost right. It wasn't far off. Actually, I took a chart. I decided to make a chart of what the distribution of ancestors looks like. And on the x-axis here, so if we look at this chart, the x-axis is each class that's loaded, and the y-axis is the number of ancestors that particular class has. And the average, on an average, we have about 12 ancestors. So the next thing I wanted to look at is what class has the most class variables, and this might seem kind of odd, but I promise it will make sense eventually. Here's an example. So here's an example of class variables, class instance variables, and instance variables. So we have two ats at the top there make the class variable, so we have one called class variable, and then we have two examples of instance variables. Actually, these instance variables are essentially the same thing. It's just that, like, when we have an instance of foo, the instance variable will get stored on that instance. Foo is an instance of class, and that instance can have class variables, or can have instance variables, so it has one. But I'm interested in these things here, these class variables. That's what I want to look for. And it's trivial to count them. You can just say like class.class variables, and it gives you a list of them. So here are the top 10 classes by number of class variables. So we have there at the top action mailbox, inbound email, and it has 24. Actually, all of these classes have 24 class variables. Hey, that's a lot of class variables. Here at HeyConf. Sorry. All right, so here's a summary of the statistics of number of class variables on each class. The mean is 0.35, so most classes don't actually have class variables. 9.2% of classes have class variables. But there's one thing I want to keep in mind when we're looking at this data, and that's comparing the number of class variables to the ancestor count. So we have here in one column the number of class variables, and in another column the number of ancestors that particular class has. What's interesting is it seems that classes that have a lot of class variables also tend to have a lot of ancestors. So the next thing I wanted to look at is most accessed class variables per request. So this is one more statistic, then we're going to move on to a different topic. I was curious which class variables are accessed the most per request. Up till now, I've shown most of the code for collecting statistics, and unfortunately, I can't do this one because I have to hack Ruby. That is step one, to record class variable accesses or class variable reads. Well, I'll show you how. This is it. I just added this patch to Ruby, and all it does is it prints every time a class variable is read. It just prints out the name of the class variable that got read. So I ran 10,000 requests through an application, and these are the top 15 class variables read on each request. I chose the top 15 because all the other ones below that, they were not accessed at least once per request. So I only care about variables accessed once per request. Now, of course, this will change depending on your application. This is just a basic application. Like, if you look at the very top here, the most one is active support logger local levels. So if you do a lot of logging, you might access more class variables. Or if you render a lot of templates, you might access more class variables. This is just going to change depending on your app. I think most of the columns here make sense. So we have a class name, class variable, number of ancestors, number of reads per request. And then I made one more column here, which is ancestors multiplied by reads. And these numbers are a little bit off just because it's floating point calculations and numbers, or Keynote kind of like did some rounding. So if we take this ancestors times reads for all of these records and we sum them, the value is 1057. So just keep that number in mind. We're going to leave this topic now, but I want you to remember this number, 1057. And I also want you to remember that many class variables usually means many ancestors for some reason. Classes with many ancestors are also fairly popular, meaning that we read from them fairly frequently. So let's move on to a totally different topic. Well, not totally different, but somewhat related topic. I want to talk about how instance variables work. We're going to start talking about instance variables. So here's a very short example of using instance variables. I'm sure we've all written instance variables. In this case, we're just reading and writing instance variables. And one nice thing about Ruby is Ruby allows you to write more instance variables. You're allowed to add instance variables to an instance. In some languages, you have to declare in advance what all of your instance variables will be, and you can't expand them at runtime. But Ruby allows you to add them at runtime, and I think that's really nice. Now, if we're going to think about how we would implement this, a natural way to implement it would be to just store a hash table. We would say, okay, let's keep a hash table with a foo instance. When we call foo.new, we create a new hash table. The hash table has a key, which is name, and then a value, which is the value of the instance variable. And as we go through and execute more, we'll read A, it can get the hash value, it reads the hash value, gets the value by name, the instance variable name, and when we add more, we can expand the hash table. Now we can say that each instance, or each object instance, has one instance variable hash. Now unfortunately, this design has a couple problems with it. The first one is speed, and the issue of speed is that we have to do a hash lookup every time we want to read an instance variable. Now, hash lookups are constant time, but the thing is, some constant times are faster than other constant times. Reading from a hash table is constant time, but doing an array lookup in C is also constant time and is actually much faster than doing a hash lookup. The other issue that we have is memory. Hash tables require a lot of space. When we need to insert, keys, like let's say each key value pair costs us 20 bytes. If we're doing that, things can add up pretty quickly. So maybe we have, let's come up with a solution to this, and the solution is let's use an array. So instead of storing instead of storing instance variables in a hash, let's store them in an array. So how would we implement that? We can implement it like this. We say, to implement it with an array, we'll introduce a hash that is stored on the class. So we'll have a foo class, and we'll store a list. We'll store a hash table on the foo class that maintains the indexes of a particular instance variable. So as a concrete example, we create a foo class. When we create the foo instance, we go up and execute initialize. Here we write the instance variable A. We check to see what is the index of instance variable A. Oh, it didn't exist, so we'll create it at index 0, and then we write to the instance variable array at index 0. So we use the index table to look up the index of the instance variable, and then we store the value in the array on the instance itself. So in this case, we'll have hello world stored at position 0 in the ivar array. And we can do exactly the same thing when we read from A. We'll look up the index, and then we'll go using that index, we'll go look that up out of the instance variable array. And we can do the same thing when we write more instance variables. We'll say, okay, we need to look up the indices for those. They don't exist, so we'll create new indices, and we'll write those values into the ivar array. So the next time we execute this, this index table actually lives between executions. So the next time we execute this code, like let's say we executed it twice, we'll reuse that index table. So it only gets created, that index table only gets created once. Now the size of an ivar array is smaller than the size of the index table, and if we have many instances of foo, then we're able to actually save memory overall by amortizing the memory that we use. I mean, I know it looks a little bit weird here because we're using a hash table and an array, but if we have many instances of foo, then we've actually saved memory for the process long term. So we use less memory overall. But we also have an issue of runtime speed, and I think this is an issue because like before we were doing hash lookups to find the instance variable. Now we have to do a hash lookup. We have to do a hash lookup and an array lookup. So the question is like, how can this be faster? And the truth is it's not faster. We have to do 2 operations. It's not faster. So how can we speed this up? The way we speed this up is by using an inline cache. An inline cache is just a cache that we store in line with the code. So right here is some example code, and can you all see the inline cache? I would guess that like, yes, you can see the inline cache. Let's wave. Hi, that's me. Okay, the inline cache is actually right here. You still can't see it? Okay, I can't see it either. You can't see it. Let's look at the actual inline cache. So the way we can see it is if we disassemble the method. So here we'll get the instance method A, and then we'll use RubyVM instruction sequence to disassemble it. Oh, I'm going to point at some code. Yeah, we get the iseqs there, and then disassemble them here. So if we print out the disassembled instructions, we'll get something like this. And here's the instruction for reading an instance variable. We see the name of the ivar. We see get instance variable, which is the... Oh, I did the arrows wrong. Oops. So here's the instruction name, get instance ivar, get instance variable. Right here we're pointing at the inline cache, and then also right here we have the ivar name. Now, this cache is stored in line with the code that we're executing. So the first time that we execute this code, it'll come through and we'll have a miss, and we'll have to go look up the instance variable in that hash table. But once we get the index from that hash table, we can write it out to the cache that's stored in line with the code. Then the next time we execute this, we'll actually do a hit, and we only have to do, we use that cached index, and then we just do an array lookup the next time. So this is how we're able to get a speed improvement out of using these inline caches. So Ruby 1.8 actually had a very simple hash lookup. The implementation was just like the very first implementation we looked at. Ruby 1.9 had introduced an inline cache. So Ruby 1.9 introduced a virtual machine which allowed us to have an inline cache. So now let's look at like how do class variables work. And to be honest, like I've been programming Ruby for at least 15 years, and I really only recently learned how class variables work. Like I didn't actually understand how they worked until I read through the implementation. So class variables start with 2 @ and they're associated with classes. And I can't remember whether or not I said this in the presentation, but please, you don't need to use class variables. Like maybe you don't need them, but sometimes they are useful. So use them, don't use them. Don't use them. Anyway, this is an example of class variables. They start with 2 ats, and you can read to them or write to them from the class or the instance of the class. So both of these cases work. So the self.read and also just the instance method, they read the same class variable. Now we use these in Rails internals like this. So if you're using, like maybe you don't use these in your day-to-day code, but Rails, the Rails matter accessor and catter accessor both use class variables under the hood. Other things in Rails that use class variables are like the Rails logger, the logger stored in the class variable on active record, and other things that we saw in the presentation, like when we were looking at those statistics. All of those things are stored in class variables. Now the way that these actually work is that each class points to a hash table, and that hash table maps class variable names to the actual value, just like we were looking at in the very first implementation of instance variables. So when we set a class variable, Ruby will walk up the ancestry tree looking for other definitions. So in this, if no definition is found, it will set it on the current class. Otherwise, it sets it on the defining class. So for example, here when this code executes, it'll go look up to A. It'll see like A doesn't have an entry for add@cvar, so it'll go ahead and set add@cvar on B. So that's the target of it. Then when we set add@cvar on C, it'll look up to B and see, oh, actually this class variable's been set on B, so I'm going to change the value that's stored in B. So it's really easy to observe this behavior. We can see that here in this case, we can see that the class variable is on B, and if we change the value from C, when we do the get against B, the value changed to 2. So we can observe this behavior pretty easily. Now, because of the way this works, a class can actually impact a sibling class. So in this example, you can see here that class C sets a class variable, but that class variable impacts the value of the class variable even when read from B. And I think this is the reason that people find these hard to use, is because when you set the class variable, it's not clear who you're impacting. It's not clear what the impact of doing that set will actually be. So here we have, just looking at this code in isolation, like if we were just to look at this code, you open this up in your editor, you wouldn't know that setting that class variable on C would actually impact module A and also class B. And I think that's why these are so confusing to use. Anyway, here we have an example of reading a class variable when it tries to read from C. So here we try to read from C, but unfortunately it's not defined there. So what it does is it has to check B, and it's not defined there, so then it has to check A, and then we find the value there, and then we're able to return hello. So this is how reads work. It's very simple. So this means that when we do a read on a CVAR, the speed of the read depends on the number of ancestors. What if we have tons and tons of ancestors? Won't this get slow? And yes, it will get slow, and not exactly for the reason that you think it will get slow. Like here's an example. Let's say we have B. B has tons of parents, and then C directly inherits from B. And then we read the class variable off of B. I can forgive you for looking at this code and thinking, oh, well, it's just going to go up to B, read the value, and then we're done with our day. Like we can just go read on C, C goes up to B, and then we're good. Like we're good to go. Like it makes sense. But unfortunately, it doesn't work that way, and that's because of some edge cases that we have. We have to deal with edge cases. And given that Ruby is so flexible, it makes for some silly and awkward edge cases that we're going to look at now. So because of Ruby's flexibility, it's possible to define 2 tables that have the same key, 2 class variable tables that have the same key. And I'm going to give you an example here. So A, in this case, A doesn't have any ancestors. We have module A. It doesn't have any ancestors, so we set the class variable on it. And B doesn't have any ancestors, and we set the class variable on it. So now we have 2 tables. Module A has a CVAR table with CVAR in it, and class B has a CVAR table in it with the same key. Now we include module A into class C. So what will happen here? When we read this value, what's going to happen? So here we have, just to show this, here we set these, we end up with two values here, and then when we include B into A, now we are pointing up to A. Okay, so when we read this, when we set like A doesn't have any ancestors, so we set all this, A doesn't have any ancestors, so we set the CVAR on A. B doesn't have any ancestors, so we set the CVAR on B. And we effectively make A, B's ancestors. That is very confusing, but yes, this is the way it's set up. So if we run this in Ruby 2.7, it'll issue a warning saying, hey, you've defined, like you've overtaken a value, and it'll actually return the top level value. And in Ruby 3.0, it'll raise an exception. So in Ruby 2.7, you get a warning, and in Ruby 3.0, you get an exception. And what this means is that in order to show you that warning or raise that exception, it means that every read has to walk every single ancestor, and it has to do that every single time you do the read. So here again is, I showed this chart a little bit earlier. Here's the chart we looked at earlier about the top 15 class variables and the number of reads they do per request and the number of ancestors for each class. And now we know why I was bringing these numbers up. Again, here's our number 1056. What this means is on every single request, we have to scan 1056 classes just to provide a warning or an exception that your application will never have, because if your application had it, it would crash. And then this is in a basic application, of course. I don't know what, like, whatever your real app is doing, it depends on the application code. Like, for example, do you use the logger? Some people do that. Do you render templates? So this gets me to the last thing I want to discuss, which is a class variable inline cache. This is a project that Eileen and I have been working on for the past few months. I'm going to introduce it here. Essentially, what we do is, just like instance variables, we store a cache inline with the instruction sequences on reads. So here we have, in these two places where we do reads on CVARs, we've added an inline cache. So here is the here's a difference between the instruction sequences. So the top box are the iSeeks. Oh, let's see. Yeah. Oh, okay. Yep. The top box are the iSeeks before the patch that we wrote, and the bottom ones are the instructions after the patch. And to make this a little bit more clear, like, I removed everything that's the same. So you can see right here, boop, boop, there, we have a new inline cache. So before this patch, we didn't have an inline cache. Now we do. Another arrow. Woo, boop. So we've integrated it here. So how does it work? The way this cache works is that the first time the class variable is read, it'll do the normal lookup process. So we'll have to scan all the way up. So it'll come in, scan all the way up, find the class variable on class A, and then what we do is we write into the inline cache a pointer to class A. Now on subsequent reads, if the next time we do the read, as long as the class hierarchy hasn't changed, we know that we can immediately just go to the target class and say, hey, I want to read, I'm going to read immediately from here. So that's basically it. That's it, folks. It was just that easy. It was not just that easy. Let's take a look at the cache impact on, oh wait. All right, let's take a look at the cache impact on performance. So this is the impact that it has on performance. So here's a benchmark where we compare reading from the top of the inheritance tree versus the bottom. So we said earlier that whenever we do a read on a class variable, it has to scan through the entire ancestry tree. So what this benchmark is showing off is the difference between the top and the bottom. So here we have a class top, and it's at the top. And we have a class bottom, and it's at the bottom. And in between the two, we have a whole bunch of other classes. So the bottom class reads a class variable that's defined at the top. And we're comparing the difference between those two. So if we run this benchmark, we'll find that when we read from the bottom on before our patch, it's, oh, that's outside of my green screen there. We'll see that it's about 3 times slower. So reading from the bottom is actually 3 times slower than reading from the top. And if we look at our benchmark results, oh yeah, added that before, woo! And if we look at the after case, after we've applied the patch, you can see that reading from the top or the bottom are approximately the same speed. These are synthetic benchmarks, like I just made this up. Let's look at maybe some more real, like actual code. Here we have active record benchmark where we're accessing the logger. And I picked the logger because I know that it's backed by a class variable. Like I knew that this benchmark would show off good results, but I wanted to do something even more real, which is in that bottom case there, we just query for the first post. So if we run this, I guess we could call this like that top logger one kind of a micro benchmark, I suppose, because I know it'll look good. So here are the benchmark results. Before our patch, accessing the logger, we could do it about 1.5 million times per second. We could also read the first post 7.3 thousand times per second. And after that, we're able to access the logger 14 million times per second and access the first post 7.9 thousand times per second. So after we've applied this patch, active record base.logger got 10 times faster, which I think is hilarious. And interestingly, just calling post.first got 5% faster. And this makes sense because if we do a profile of this thing, so like let's say we profile post.first, we'll find in here, like this is just a stack prof of analyzing post.first, we'll see that we have active record base legacy connection handling and active record base logger. Those two things depend on class variables. They just read from a class variable, and they account for approximately 8% of the time when loading a record. Now, if we do the profile after we've applied the patch, we will find that those two values have gone down. So here they went from 8% of the time down to 3% of the time, so the 5% of time, it adds up. One thing that's interesting though is even after we've applied this, like thread.current apparently takes 8% of our time, so I'm not sure why that is so expensive, or I think we should probably be looking into that, but it is actually surprising to me that thread.current is a bottleneck for loading a record. Anyway, class variables are much faster with the patch that we worked on. They went from an ON operation, depending on the number of ancestors the class has, to an O1 operation. And now it is time for me to wrap it up. So we made jokes. We made really good jokes. I moved on to a rantish section, which the point of this rantish section was find the language and framework that fit you best, and for me that's Ruby and Rails, and get good at those things. We looked at some weird Rails statistics, and then we looked at implementing some performance improvements. And I think that this was a really long and winding road to get to this point, but actually, the reason I took this long, windy road to get to these performance improvements is to show that, like, you, and I mean, yes, you in the audience, you all can be finding these and making these improvements too. All this code that's in Rails was just written by humans, and you are humans too, which means you can learn it and understand it. I really want to say thanks to J.A. Hawthorne, Eileen Codes from GitHub. We've been working with them on this stuff. I also want to specifically give a shout out to Jean Boussier and the Code Foundations team, my team at Shopify. Again, I work for Shopify and we're hiring. Woo! Yes, we are. Thank you so much, and I hope that I can see all of you actually in person next year. Oh.